welcome to the course Advanced Reaction Engineering. So, we are going to start the discussion on solid catalytic reactions, the reactions and the diffusions. We already have discussed in our previous class the reactions, diffusions in a solid spherical catalyst. The mass transfer operation is there or diffusion is there. So, with the reaction, so based on that we have derived the concentration profiles for a solid catalyzed reactions, and after that we discussed about that internal effectiveness factors, that is eta, that we have discussed. And now today we will discuss about the non-isothermal effectiveness factors, falsified kinetics, Weisz-prater criteria, Mears criteria, and one numerical example that we will discuss. So, effectiveness factors, that is very important. So, means when gas and solid reactions is there, so means solid spherical particle is there, and if we are conducting the reactions, so over the surface of the catalyst, so then the surface concentrations is always greater than inner concentration or inside of the pore concentrations. Therefore, the rate out, if we consider based on the surface concentration of the reactants, and if we consider the rate based on inside particle or inside pore concentration of the reactant, so then the rate would be different. Okay. So, therefore, also means the reactions we are considering for a particular gas and solid reaction system. So, there the reactions may be exothermic or endothermic reactions. So, since the reactant molecule surface and inside of the pores both are different, therefore, rate of reactions would be different, and if any reactions is exothermic, then heat formations would be theirs, and therefore, means effectiveness factors, if we consider means do not consider the diffusions, then the effectiveness factors of course would be 1. So, if we consider the diffusions, then rate would be different at different locations since concentrations are different. Therefore, the effectiveness factor sometimes means maximums it may be 1, but it also may be greater than 1 sometimes or in some cases. So, when reactions is exothermic and non-isothermal. So, means reactions is exothermic means inside of the pores having higher concentrations, higher temperature formations is there due to the reactions, high rate of reactions. So, in that cases, so if thus, and also if you are not able to means make it isothermal when the reactions is there, so then more heat would be there inside of the pores than outside. So, therefore, the effectiveness factors may be sometimes greater than 1. So, okay. So, when the external surface temperature of pallet is less than the temperature of the inside, since the reactions is exothermic inside of the pore, their temperature may be higher than pallet outside temperatures, and the rate of the reactions inside of the pallet is greater than that of surface. Okay. So, then these effectiveness factors we usually express in this way. So, in few cases it may be greater than 1. So, how and what are the cases? So, how we can express that? So, that we will discuss. So, the effectiveness factors can be greater than 1, and it depends on the two parameters, that is one is the beta, another one is the gamma. So, beta is the Arrhenius parameters, that is expressing in terms of E by R Ts. Ts is the surface temperature, is the activation energy of the systems, and beta the parameter, that is the temperature difference, T max minus Ts. Ts is the surface temperature, and T max, that is the inside of the pores or inside of the surface of the catalyst when exothermic reactions may be there or proper heat dissipation is not there due to the thermal conductivity natures of that materials. So, then if the thermal conductivity of the material is poor, so in that case, so then the some temperatures differences would be there. So, beta we can express minus delta H Rx, that is heat of reactions, effective diffusivity, surface concentrations, and thermal conductivity of the materials and surface temperature. This way we can evaluate that. So, it actually indicates this is the ratio, means two temperature ratio, that is the difference, maximum temperature difference and surface temperature. So, if the when this means temperatures changes or differences is there inside and outside of the particles when reactions is there, it depending upon that. So, instead of one steady state, means whenever we conduct any reaction, so we should expect that one steady state should maintain, but when in such cases when effectiveness factor is more than 1. So, in that cases phi should be less than 1 and beta should be greater than 0. If these two parameters, if we are able to find out and we measured that phi is grading for that particular system which is less than 1 and beta is greater than 0.2. So, then in this cases we can say that multiple steady state may exist in that system. And in multiple steady state, how we can say that it is existing. So, if we plot Theli modulus, so Theli modulus and effectiveness factors, how they are related, the correlations we have developed in our previous class. So, if under these conditions, if phi is less than, this is the phi in the x axis, that is the Theli modulus, if this value is less than this, means within these regions, and beta 0.2 greater than 0.2. So, beta equals to minus 0, 0.1, 0.2, 0.4 and 0.6 at different beta value. If we plot effectiveness factors and Theli modulus. So, then you can see that when beta greater than 0.2, so here you can see multiple steady state exist. So, in this case here is steady state, here is also steady state, multiple steady state each exists. So, under this means if we are able to measure phi and gamma value, and if phi multiplication of phi and gamma means 4 into 1 plus beta, this value should be greater than beta into gamma. So, it has been proposed by this Weisz, this criteria has been means developed by Weisz, and if this criteria is fulfilled, then no multiple steady states exist, means whenever the systems will design or catalyst we have designed. So, multiple steady states should not be present in our system. So, one steady state should be there. So, these are the things, means phi value and beta value should be such that there is no multiple steady states exist, and non isothermal effectiveness factors or means temperature gradient, that is the temperature changes or differences should not be there inside of the reactor. So, that whenever design a catalyst reactors we should means follow these things, okay, or we should maintain. So, now we are going to falsified kinetics. So, what is falsified kinetics? So, that already you have discussed that effectiveness factors is very crucial or very important parameters with the Theli modulus. So, means whenever we conduct any reactions, we usually consider the bulk concentration or surface concentration of the reactants, and based on that we usually put that concentrations in the rate equations. Rate equations usually we express this CAS this way, we usually express. So, here the concentrations we usually express the surface concentrations, but when catalyst is a spherical and inside pore is there, so here concentrations would be different. So, if concentration at different location inside of that particles are different from the surface concentrations, so then rate would be different from inside to the outside. So, therefore, effectiveness factor is coming. So, it indicates, so the either the rate to rate means difference, if that means effectiveness factor is 1. So, then we can say that there is no diffusion. Most of the cases we usually ignore the diffusion components. So, we if we do not consider the diffusion part, so then the rate measure rate constants and activation energy, that would be different from the actual rate. So, usually let us say this is the rate equations, let us say. So, this is the measure rate rate of reactions minus R A primes, and with the gas phase concentration that usually considered, and this type of things we usually consider minus R A prime equals to minus R A S prime equals to K n prime K prime n and C s to the power n prime. So, if at this particular T1 temperature, if we plots log plots of this and concentrations, so then the lines would be like this at particular temperature T1. If we do the reactions at T2 temperature, then it would be like this. So, here from the slope we can find out the n. N is the rate means order of the reactions. So, and from the specific reactions rate or rate constants we can find out the activation energy. So, here what is happen. So, this is the cases, means normally using the surface concentrations or bulk concentration, both are the same, most of the cases we consider, and eta that is means equals to 1, so most of the cases we considered. But when we consider the diffusion, so diffusion is there, so then eta may not be 1, so it should be less than 1. So, it has some value maybe 0.9, 0.8, 0.6 like that. So, it may be some different value. So, whence diffusions does exist in the system, so then the rate would be different from the measured value. Okay. So, the rate law for the measured rate equations, when eta equals towards effectiveness factors, we are considering eta equals to 1. So, in that case the rate would be like this, minus R A prime equals to k n prime C S n primes. So, then but this is the measures, the way we do means most of the cases we ignore the diffusion component, therefore, it is coming this. So, whence diffusion is there, in that case what would be the means if diffusion does exist in the system. So, then the actual rate that we have to measure by using this way, means the rate is this. So, R S prime equals to this. So, then this rate equations we have to use, this is the true rate of the reactions. So, usually we use minus R A prime equals to k n C S n. So, this way usually expressed, but instead of that this is the this way we usually apparent or measured rate. So, true rate is this, means effectiveness factors we have to include here. So, once we include this, so then when true rate of reactions, if it is rate is this rate of reactions, effectiveness factors we are adding in the rate equation. So, effectiveness factors for the large Theli modulus, when the Theli modulus effectiveness factors and Theli modulus we have discussed, when Theli modulus is very large value. So, then diffusions would be theirs. Okay. So, when diffusion is there and then Theli modulus and effectiveness factors related is like this, and Theli modulus we can express this way, phi n square equals to this for nth order reactions. Okay. So, these phi n's these equations was for first order reactions. If we express for nth order reactions, it can we can write the effectiveness factor is this way. Okay. If we put n equal to 1, then it would be converted into this. So, this is for in general effectiveness factor and Theli modulus. So, then now for nth order reactions phi n, here it would be n. So, phi n we are substituting here. So, from here, so then we can get phi n equals to this. Okay. So, eta equals to this, but after substituting phi n in here. So, this eta we can substitute here. Okay. So, once we substitute this for large Theli modulus value, so large Theli modulus value means diffusions exist and eta less than 1, okay, eta value less than 1. So, in that case if we means rearrange these equations and simplify these equations, the equations would be like this, when diffusion is there and eta values would be less than 1 and for large value of Theli modulus. Okay. So, in that case the true rate of reactions rates is this, and usually we measures or apparent rate this, there we are not considering Theli modulus or effectiveness factors. Okay. So, this both we are means this R A primes we are substituting here. So, then we can write this. Okay. So, in the left hand or this component is for true rate of the reactions and this part is the measured or apparent rate of the reactions. So, this is equations 1 and this is equation 2, let us say. So, both the rates would be the same. So, then we get these equations. Okay. So, here now left hand side and the right hand sides, if we only just considering concentration terms, these terms concentration terms left hand side and right hand side, since both the rates are equal. So, then left hand side concentrations and right hand side concentrations if we correlate. So, then we can see that n prime equals to n plus 1 by 2. So, n prime is the apparent rate that we have, n prime is the apparent rate and n is the true rate, true order, n prime is the apparent or measured order. So, here n and n prime, if you see, so n equals to put 0, so n prime equals to half, n equals to put 1, so n prime equals to 1. So, like that if n equals to put 1, n prime equals to 1.5. So, true order is this. So, means this is the suppose if we measure the order of the reactions by considering minus R A prime equals to K C S to the power n. So, these rate equations we have used and without considering the diffusion components. So, then so the order would come let us say a half order. So, actually the reactions is 0 order. So, if it is first order then also it would be first order. So, for case of first order reactions, so there would be no changes of that orders, but in other cases other than first order reactions, so the order would be different. So, now not only the order of the reactions, with that activation energy also would affect how that. So, if we true specific reactions rate or reactions rate constants, if we express in terms of activation energy, it is the activation energy, and apparent or measured specific reaction rate if we express in terms of activation energy. So, this is true, Et is the true activation energy, and E apparent, that is the measured or apparent activation energy. Okay, so, this is apparent and this is true. Okay, so, now this Kn and Kn primes both they are substituting in these equations. These equations we have derived, these equations we have derived, and in that equations Kn is there and Kn prime is there. So, both are we are substituting or replacing in terms of this. Okay. So, after that if we simplify and take log in left hand side and the right hand side, so you can see that this activation energy terms we can take out from here and here, left hand side and right hand side. If we compare the temperature dependency terms from the right hand side and the left hand side, the activation energy equal to the twice of the apparent or measured activation energy. So, activation energy apparently whatever we have measured, and the true activation that would be almost a double of that. So, order and activation energy both would be the different if we consider the effectiveness factor, Thele modulus or diffusions for a particular systems. So, thence it would be different, and this is due to the internal diffusion limitations are present, okay, and is referred to as distinguished or falsified kinetics. So, this is means the kinetics we have means derived or we have measured the order activation energy for a systems without considering the internal diffusion of the system. So, then that would not be exact or accurate value we will get. Okay. So, therefore, always whenever talk or means discuss about by considering solid catalyst and reactions is going like this. So, solid catalyst is there, it has a particular spherical size or size. So, in that case we always consider the diffusion of that internal diffusion part also. We have to consider whether there is internal diffusion is exist or not. So, depending upon that particle size, if very small particle size diffusion is not exist, internal diffusions reactions rate would be controlled, but when is definite or defined particle size is there. So, in that case diffusion may be exist internal diffusions. So, in that case the reactions order and activation energy that will calculate. So, that would be little bit different from actuals. Okay. So, now Weisz-prater criteria for internal diffusion. So, how or we can measure, suppose in a spherical particles or catalyst solid particles we have taken for a particular reactions. So, we can say that there is internal diffusion may exist or may not be exist. So, then if we quickly estimate means the systems the reactor we have reactions we have and we know that dimension or other parameters of the catalyst particles. So, this then if we want to measure quickly estimates that whether there is internal diffusion exist or not. So, for how we can measure that. So, for that this Weisz-prater criteria is exists. So, there are some parameters value we have to put, and if satisfy this Weisz-prater criteria, then we can say that the internal diffusion does not exist in the system. So, the catalyst we have designed for the particular reaction. So, that is okay. So, we can use that. So, here internal effectiveness factors that way effectiveness factors and Thele modulus, these equations we have discussed or we have derived. Okay. So, here this is eta is the effectiveness factors and phi is the Thele modulus for first order reactions. Okay. So, here this phi 1 square, if we are taking into the left hand side, then it is giving eta into phi 1 square equals to rest of the terms. So, this eta phi 1 that is called Weisz-prater parameters. Okay. So, left hand side this component is called Weisz-prater parameters. So, Cw, that is the Weisz-prater parameter, that is eta and phi 1 square. So, if we are able to measure eta and phi for a particular system, so then these two components we can substitute here, we can say that it has some value would come. So, considering that or means analyzing those Weisz-prater parameter value, we can say that whether there is internal diffusion exist or not. Okay. So, this actually Weisz-prater criteria, eta equals to observed actual rate of reactions to the reactions rate evaluated at CAS and multiplied with phi was square, that is the Thele modulus. Thele modulus reactions rate evaluated at this and diffusional rate. So, it actually Weisz-prater criteria indicate actual reactions rate to the diffusional rate. So, actual reactions rate to the diffusional rates, that equals to Weisz-prater criteria, or that indicate what it signifies. So, now eta equals to this observed rate to the surface conditions or this rate evaluated at CS conditions, means concentration, surface concentrations of that reactants, considering that the rate evaluated, and this is phi. Okay. So, phi 1 square, that is for first order reactions, this is for nth order reactions, phi n square is equals to this, and we can simplify this. So, here k n we can replace in terms of k n single prime into rho c. So, k n and k n prime rho c S A, rho c means density of the catalyst, surface area of the catalyst, k n double prime. So, that we have discussed in our last class. So, how they are related means the rate constants in terms of volume, in terms of surface area, in terms of the mass. So, that way we can express. Okay. So, therefore, here's R A prime equals to k n prime into CAS. Okay. CAS, that way we can write. Okay. So, here k n we can substitute k n prime into rho c equals to this, and here if we multiplied both this eta and phi n square. So, Cwp, that is the Weisz-prater parameter, equals to this So, here we can get this and this with eliminating. So, R observed equals to R A minus R A prime observed equals to rho c r square by d E A c. So, this is actually the parameter that way you can find out, or the observed rate we have usually minus R A prime observes for a particular reactions, the rate we know, density of the catalyst if you know, catalyst particles radius, the spherical particles it has particular radius if you know, effective diffusivity you know, surface concentration of the reactants we know. So, then this way also by putting this value Weisz-prater criteria easily we can find out, it has some value would come. So, if this value numerical value, if it is less than 1, so it may be less than 1 some value, it may come 0.8 let us say, or it may come 1.2. So, if it is less than 1, it is greater than 1. So, if it is less than 1, so there is no diffusion limitation exist in the system. So, quickly you can estimate. So, we have observed rate, density of the particles, radius of the particle, effective diffusivity and concentration, surface concentration of the reactants we have. So, then easily we can putting this instead of finding eta and phi. So, Weisz-prater criteria easily we can find out Wp or Cwp Weisz-prater parameter if it is less than 1. So, there is no diffusion or internal diffusion exist, no concentration gradient exist in the or within the pellets. So, the catalyst pellets we have taken. So, here CAS surface concentration, here Ca. So, CAS minus Ca, that is the concentration difference. So, this difference does not exist, means everywhere inside outside of the catalyst particles having same concentration. So, then by that way we can say that there is no diffusion limitations does exist in the system. So, the system means catalyst, we have designed the particle diameter that is appropriate for our system. If it is greater than 1, so its value has come, then internal diffusions exist and that is limiting the reaction severely. So, then the catalyst particle size you have considered to for our particular reactions for industrial scales. So, then we have to change the diameters or radius of that particular catalyst. So, by that way we can, or concentrations of the reactants you have taken, so you have to change that. So, by that way we can means quickly estimate whether internal diffusions exist in our systems or not. Okay. So, there is some other things apart from that is called Mears criteria. For Mears criteria for external diffusion, this is for external diffusions, okay. External diffusion. So, here catalysts and pores, if surface concentrations DSC and CAB, this is the bulk concentration. So, whenever a reactant substance is there, this is bulk concentrations, this is surface concentration, this is pore concentration or inside of the pores. So, here some barrier is there, within that means concentration changes is there, means if reactions is very fast, reactants will be consumed very fast. So, here the flow rate means reactants will come here. So, before that it is disappearing or converting into the product. So, then some changes are there, CAB minus CAS, maybe some concentration changes are there. So, if there is concentration changes are there, say then diffusions would be there, that is called external diffusion that we have discussed. So, the measured rate of the reactions in terms of kg of catalyst, kilomoles per kg catalyst per second, if the mass transfer from the bulk gas phase to the catalyst surface can be neglected if under these conditions. So, Mears has proposed and these correlations has been proposed. So, if minus R A prime rho b R n K c and C b less than 0.15. So, then external mass transfer effect can be neglected. So, if we know the observed rate, density of the bulk density of the catalyst, n is the order of the reactions, R is the catalyst particles radius and Kc is the mass transfer coefficient, concentration of bulk concentration, density of the catalyst beds if we know. So, then we have to put it here and then the value will be evaluated. If it is less than that, then there is no external diffusions exist in the systems, means the reactors we have considered. So, there is it does not exist. So, then we can consider and we can use that particular reacting systems or reactors, reactions, catalyst for our system. So, the things will come means conversions or other things that yield selectivity, everything will be acceptable. So, apart from that, so Mears also proposed another things, that is temperatures. Bulk fluid temperatures will be also virtually the same as the temperature external surface of the pellets. So, bulk fluid temperatures. So, here if this criteria is fulfilled, means if we know heat of reactions, bulk density, radius of the particles, activation energy, heat transfer coefficients and gas constant. So, if after putting these parameters in here and if that value is coming less than 0.15, then also we can say that with the internal diffusions. So, the bulk fluids and the catalyst surface fluid, the temperatures changes does not exist. Okay. So, having the same or same temperatures means fluid temperatures and particle temperatures having. So, now one numerical examples also we can means discuss about how to find out the Thele-modulus, effectiveness factors and particles radius or particle size would affect. So, here one example, let us say this is a first order reactions that would be carried out in a reactors. Let us say this is our reactors, here is going to be reactions. So, here this is the catalyst particles we have taken. So, these catalyst particles having same catalyst, once having this radius that is 0.01 meter particle size pellet radius and another same materials, but different particles we have taken. So, both are same compositions, but the particle size are different. So, run once we have considering these particles, and run 2 have considered this considering this particle of catalyst inside of the bed. Okay. And corresponding rate, if these particles, the rate was measured this, and observed rate for this is this, when this catalyst was used for the same reaction. So, then the rate was this. Okay. So, now we have to find out the effect Theli modulus, we have to find out, effectiveness factors we have to find out, and how small, means whether the particle size you have taken 0.01 meter or 0.001 meters, that radius we have chosen two different, whether it is suitable or not, if you whether there is internal diffusion exists or not. If internal diffusion exists, then at what particular size of catalyst we have to consider, there we can eliminate the internal diffusion, that we will discuss. Okay. So, this is the correlations that we have discussed, effectiveness factors and Theli modulus, how they are related. So, for run 1 and run 2 we can write this, means other parameters are the same. So, here this for catalyst 1 and run 1 and run 2, if we write this way for run 1's phi 1 for catalyst 1 and this is phi 1 for run 2. So, 2 indicate run 2, 1 indicate run 1. So, phi 1, that is the reactions n equals to 1, therefore, this is 1 for both the cases, same reactions, this is for run 1, this is for run 2, this is Theli modulus. Okay. So, now if we write, means rho c d c s both are the same for both the catalysts. So, when catalyst particular changes, these are the components should be vary, for particle 2 this, particle 1 this. So, these expressions we can write this way for two different particles. So, Theli modulus equals to this, that we know. Okay. So, now Theli modulus, here you can see Theli modulus directly proportional to the, from these correlations we can write directly proportional to the R. So, phi 1 1 by phi 1 2 equals to R 1 by R 2. So, R 1 and R 2 both are knowns. So, that ratio equals to 10. So, phi 1 1 equals to 10 times of phi 1 2. So, that we can get from here. So, how Theli modulus from one shape of particles to the another shape of particles will vary for the same reactions. Now, if we substitute this phi 1 and phi 1 1 and phi 1 2 by one parameter. So, then from here we can get, after simplifications, phi 1 2 equals to 1.65 we can get after simplifications. So, this rate is given, R 1 R 2 is given, R 1 this is R 2, this is minus R A 1 primes minus R A 2 prime is given. So, in the left hand side parameters are given. So, phi 1 1 equals to phi 1 2, that we can substitute here, then phi 1 2 we can get, that is equals to 1.65. So, for second particles the Theli modulus, for similarly for say first particles we can get this. Okay. So, we can evaluate this first, then we can evaluate this. So, now corresponding internal effectiveness factors also we can find out if you know this. So, this is the definition of the internal effectiveness factors and Theli modulus relationship. This, if we, this value is here, if we put and phi 1 value, then eta would come. Okay. So, then eta 2 eta 1 we can get. So, effectiveness factors for two different size of particles are these. So, when R 2 means a smaller particle is there, effectiveness factors you can see very small, when particle size is large, effectiveness factor is very small. So, means some diffusion does exist, it indicates. So, how we can eliminate this? So, if we consider that effectiveness factor is close to 1 or 9.599, so in that case we can above 90 we can then eliminate internal diffusions, we can eliminate. Okay. So, in that case we assume that, and putting this in the equations, effectiveness factors this in these equations, eta equals to, we are considering this and this we are taking, and here eta equals to 1.95 we are putting instead of 1, 1 also we can put, but here we are putting 0.95. So, if we put 0.95, so then phi 1 3 we can calculate. See, here's the particle size for R 1 3 R 3 particle 3 size we have to find out R13 phi 13 we have measured from here by considering eta equals to 0.95. So, then R3 we can evaluate if we know phi 11 equals to some value for R1 part size of particles. So, R3 we can find out that equals to 5.5 or into 10 to the power 4 meters. So, our particle size if it is 0.55 millimeters is there. So, then means particle size R3 equals to 0.55 mm. Then so we can say that eta equals to close to 95. So, internal diffusions does not exist or we can eliminate that under these conditions. So, means particle size here it would be mm I think no matter. So, thank you. So, today is up to this. So, I think we have discussed non-isothermal effectiveness factors we have discussed, falsified kinetics we have discussed, and then we have discussed Weisz-prater criteria for internal diffusions, Mears criteria for external diffusions, and we have considered one numerical example and we have solved that to get an idea about effectiveness factor, Theli modulus and particle size. So, I think this part is over. So, thank you. So, something else we will discuss in our next class. Thank you.